Good morning everyone, and welcome to today's worked exam answer question. Today's question is for Year 13 students who have been having a look at carbonyls chemistry, either at the end of Year 12 after your exams perhaps, or at the start of this year. And in this question we're going to have a look at different ways that we can make esters. So we are going to be using an alcohol in each case, but we're going to be thinking about using either a carboxylic acid, an acyl chloride, or an acid anhydride. And then at the bottom it's getting us to think about sort of some of the benefits of using one over the other. So we've got to compare using an acyl chloride to using a carboxylic acid, and then using an acid anhydride instead of an acyl chloride. So there are different ways that we can make esters, but one thing that's really important to, I guess, take note of today is that whichever kind of secondary agent we use, the atoms will be the same in terms of which comes from which reactant. So in the first question we've got to write an equation for the formation of methyl propanoate, and they've given us the formula for that there, from methanol and propanoic acid. So I guess the first thing that I wanted to do is just showcase which atoms are going to come from which reactant, and this will always be the same when we're making an ester, regardless of which of these three starting materials that we use in addition to the alcohol. So from the methanol we're going to get that CH3 there and the O there. So the methanol is going to lose its hydrogen, and then from the propanoic acid in this case we're going to get the CH3, CH2, and then the C with the double bond O. And the alkyl part and the C with the double bond O will always come from either the carboxylic acid, the acyl chloride, or the acid anhydride, and the alcohol will always bring the single bonded oxygen and then the alkyl group there. And you can see that when we name an ester, which is a little bit odd, we name it using the length of chain that's attached to the single bond oxygen first, that comes from the alcohol, which is on the right hand side. Then we go with the number of carbons from the original carboxylic acid to give us propan, and then the O8 part is what tells us that this is an ester. So it hasn't said anywhere in this question that we're making an ester, but I know that it's an ester based on that O8 there. Now when we write an equation for the formation of this, we need to also know that the process of making esters in this way is reversible. So we're going to need a reversible arrow, and we also need to know where the other atoms from the alcohol and the carboxylic acid are going to go. And if the alcohol is losing a hydrogen and the carboxylic acid is losing its OH, then we're going to get water as our second product. So methanol, CH3, OH, plus propanoic acid, CH3, CH2, COOH. Reaction is reversible, so we use the reversible arrow, and then that's going to give us the ester, the methyl propanoate or propanoate, however you choose to say it. So the C and the O from the propanoic acid, and then the OCH3 from the methanol, and then we're going to get water as our second product. And that is one way that we can make an ester. And when we think about some of the questions at the bottom about the advantages of different methods, the thing that's not great about this is the fact that it's reversible. So if we were only wanting to make the ester, this is probably not a good way to do that, because once we've got to dynamic equilibrium, we're always going to be sort of losing some of our ester, and whilst we can shift the position of equilibrium by changing temperature or concentration, we're never going to get 100% of the ester here. I don't think the position of equilibrium will ever lie 100% on the right hand side, because you always will have some product going back towards the reactants, because the equilibrium will be dynamic and both reactions will always be occurring. So that's not great, but we'll come back to that in part DI. So next way that we're going to make an ester, we're still using methanol, but this time it's wanting us to use propanoyl chloride. And we have to, in terms of the demands of this question, be naming and outlining a mechanism for this reaction. There is no mechanism that we need to know for making an ester this way via esterification, but there is a mechanism that we need to know for making the ester this way. We're making the same ester, methyl propanoate. So again, the methanol is going to give us the OCH3, and the propanoyl chloride will give us the CH3CH2CO. So we are going to make the same ester. We're going to get a different second product though, and this reaction is not going to be reversible. So this is where sort of knowing your connections between different homologous series is going to be important, because as soon as I see an acyl chloride, I know that we're going to be using the nucleophilic addition elimination mechanism. And that's because that is the only mechanism that we would ever be drawing with an acyl chloride as kind of our starting material. I mean, we do use acyl chlorides in electrophilic substitution if we're doing Friedel-Crafts acylation, but I would say the main product there is the benzene ring, and the acyl chloride is used in the formation of the electrophile, so a little bit different. But propanyl chloride, thinking about making an ester, there's no benzene involved, it's going to be nucleophilic addition elimination. So first of all, what is an acyl chloride? An acyl chloride has the C double bond O adjacent to a chlorine atom bonded on there like that. So it's not an OH like in a carboxylic acid, it's a chlorine. And the methanol is going to be our nucleophile, because within the OH, the oxygen will have a lone pair. And when we're doing anything nucleophilic, the nucleophile wants to donate a pair of electrons, and it's going to want to do that to something that is either positive or partially positive, which is going to be this carbon here, because this oxygen is much more electronegative than the carbon, so the carbon will be delta positive and the oxygen will be delta negative. And this is also a polar bond as well, where the chlorine is more electronegative, so this is going to be delta positive. You don't have to show the partial charges, but I'll put them on now for reference. But in an exam scenario, you wouldn't need those. You would need the lone pair on the oxygen, and you would need to show that that lone pair is going to form a bond with the carbon. And then in this first step, because we're doing addition, we can't immediately get rid of the chlorine, because that then wouldn't be addition elimination, that would just be substitution straight up. So what we need to do if we want to add the nucleophile on and have nothing leaving is we have to open up that C double bond O and make it into a single bond, and then nothing is leaving, and that would class as an addition step. And that's the same as the first step in nucleophilic addition as well. Then we're going to get an intermediate structure, which you'll get a mark for drawing, so long as you've got the charges and all the bonds in the right place. So the carbon to oxygen is now a single bond up there. We've still got the carbon bonded to the chlorine at this point, and then the nucleophile has added itself on via the oxygen of the OH, and then we've got the H and the CH3 still attached to the oxygen as well. Now, oxygen wants to be forming two bonds, ideally, with its two lone pairs that are not involved in bonds belonging to the oxygen. Now, in the oxygen at the bottom, where the nucleophile added on, the oxygen is using its lone pair to bond to the carbon. So it's now got three bonds and only one lone pair, which it's not a fan of. Also, as its lone pair no longer belongs to it solely, sharing them with the carbon, this oxygen will be positive, and we're going to need to take away a bond to replenish its lone pair. The oxygen at the top took both electrons from that bond, which means that it took its own electron back, but it also then took carbon's electron with it. So this oxygen now has one more electron than it did initially, which is why that will be O minus. Now this still has lone pairs. It will have two. We only need to draw one. that lone pair is going to reform the double bond. And this is where nucleophilic addition elimination becomes different from nucleophilic addition. In nucleophilic addition, that lone pair would then attack a H+ to become an OH group. Here, we're reforming the double bond because the ester still has the C double bond O in it. We're just changing what comes after the C double bond O from a chlorine to, in this case, an OCH3 to make our ester. So when the double bond reforms, the chlorine gets eliminated. And then we just need to sort out this oxygen at the bottom, and we're going to do that by breaking the oxygen-hydrogen bond, and it has to be that bond. You won't be breaking bonds between oxygen and carbon to release a kind of a CH3. This H will leave instead. Both electrons are going to oxygen, so this will leave as a H+. This is going to leave as Cl-, so the second product that we're going to get here is HCl. Now, I'm not going to draw the product of this mechanism because I don't need to. There's only one thing we can make from this mechanism, and that is methylpropanoate. I'm therefore not going to write plus HCl either. You're not going to get any marks for that. The marks are going to come from one for the name, one for this curly arrow, one for that curly arrow, one for the intermediate structure with the correct charges, and then annoyingly for these 3 curly arrows, that's your final mark, and that makes 5. So the only times you'll need to draw the products is if there are multiple products that can be formed, and then you need to show which product you formed in your version of the mechanism. Okay. Then we're told that instead of using an acyl chloride like propanol chloride, in part C we're told that we can use propanoic anhydride. We're still going to make the exact same ester. As you can see here, it says that the propanoic anhydride can be used instead in the preparation of methylpropanoate from methanol. So we're still using the same alcohol, and we're still using a carbonyl compound that has the C double bond O that we can put into our ester. Now, in this question, we would never be drawing a mechanism for this. You might have been asked to write sort of an equation to show how the propanoic anhydride would react in place of the propanol chloride, but never any mechanisms for those starting materials. But here we're just being asked to draw the structure of the propanoic anhydride. It hasn't specified a type of structure, so we could do it as displayed. We could probably do a mix of displayed and structural, or we could do skeletal. I'm not sure why you would choose to draw skeletal, but you can if you want to. Now, the thing we have to remember with acid anhydrides, well, I guess there's 2 things. One, we need to know the functional group, which is that we've got a C double bond O, and then a single bond O, and then on the other side of that, we've got another C double bond O. So that's the functional group for an acid anhydride. And then the other thing that we have to remember is that there'll be a plane of symmetry through that central oxygen, and you will always have the same number of carbons on each side. So when we call this propanoic anhydride, the whole thing will actually have 6 carbons. The prop is referring to how many carbons are on one side of that plane of symmetry. So that means I'm going to then need a C with 2 H's, my CH2, and then I'm going to need a CH3. And that will give me my propan. And then because of the plane of symmetry, I'm then going to need the same on the other side. So that is something you have to remember, because if they give you the name of an acid anhydride, you might have to draw its structure like this and remember there's 3 on each side. Or if you were given this and you were asked to name this, you wouldn't want to be naming it hexanoic anhydride, because we'd only be counting the 3 carbons on either side. Okay. Now we're going to think about advantages of making one thing, using one thing over another to make this ester. So again, we're still thinking about the same ester at this point. So here we've got to give an advantage, only one advantage, of using propanoyl chloride instead of propanoic acid. So why we might want to use this instead of this. Now there's some reasons why we wouldn't want to do that, like the fact that we're going to make hydrogen chloride as a byproduct here, which is not very pleasant at all, whereas here we make water. That is a lot safer. However, it's not asked for a disadvantage, it's asked for an advantage. So the advantage is going to come back to this reversible arrow here. We will make the ester from the acyl chloride, and that will not go backwards to regenerate the reactants. So that is the advantage here. So no reversible reaction, and therefore no equilibrium established. And in addition to what I said before about obviously losing some of our ester because it will react with the water and go back to making the original reactants, even if we were okay with that and then we had this equilibrium, we'd then have to be able to separate the ester out from all of the other things. Whereas if we can force the propanol chloride and methanol reaction to completion, making sure that, you know, we're kind of using up all the reactants, the hydrogen chloride will be a gas. And yes, I suppose if there's like an aqueous solution of methanol in the first place, then that could dissolve to make hydrochloric acid, but it would also be a bit easier to separate those things than having to separate the ester when you've got all of these other products and reactants present at the same time. So yeah, there's lots of benefits to it not being a reversible reaction. If you didn't know that that was a reversible reaction, that becomes a harder question. And then the next one, which is the one that we're more used to seeing if you've been having a look at exam questions on this already, is to give one advantage of using propanoic anhydride instead of propanol chloride in the industrial manufacture of methyl propanoate from methanol. So when we're thinking about this in industry, we prefer to use acid anhydrides, even though the reaction is a little bit slower. That's obviously not an advantage, but the main advantage of using propanoic anhydride is, as we can see in the structure we drew in part C, no Cl. That means that when this reacts with methanol, we will still make our same ester, the methyl propanoate, but rather than the byproduct being HCl, it's going to be a carboxylic acid, because you're going to have all of this other side of the acid anhydride, which will take the hydrogen that comes off from the nucleophile to make a carboxylic acid. That's a lot less dangerous than producing HCl. So that is one advantage. Another advantage of using propanoic anhydride is that the acid anhydrides are cheaper than the acyl chlorides, so that's also good. The reactions are much easier to control than they are when we use the acyl chloride. So that's a good thing as well. So I'm going to give as my advantage no HCl fumes released, which are toxic, as carboxylic acid byproduct formed instead. And there we have it. So there's my word exam question for today, looking at different ways that we can make esters and the advantages of some of these different methods. If anybody has any questions, of course, please do leave a comment on this video. And if anybody has any requests for future videos, again, please let me know. Thanks, guys.